So hi everyone, welcome to our discussion of chapter 5. We've talked about Newton's first law in chapter 4, and now we're going to move on to his second law, which involves force and acceleration. So the objectives, what we want to learn in this chapter, we want to be able to define and explain net force. We want to state the relationship between acceleration and net force. We want to be able to state the relationship between acceleration and mass. We want to distinguish between the concepts of directly proportional and inversely proportional. State and explain Newton's second law of motion. We also want to talk about friction, how it affects a stationary and a moving object. Also discuss pressure a little bit in terms of force. We want to be able to talk about Newton's second law and why free fall doesn't depend on the mass of an object. Also, what's happening to the acceleration and the speed of a falling object when air resistance is involved. So just a quick review on acceleration. Recall that acceleration defines how quickly motion changes. So anytime we have a change in motion, whether we're speeding up, slowing down, changing direction, all those are accelerations. We define acceleration by how much that velocity changes in a certain time period. So we've talked about acceleration before. Now we're going to be talking about what causes that acceleration. And the cause of acceleration is force, more specifically a net force. And you can think of that in terms of a hockey puck, knowing that if you put a force on it with a hockey stick, it's going to continue along the ice with a constant motion until another player stops that motion with their stick, also obviously applying a net force to the puck to make it going from constant velocity to being stopped. So acceleration depends on the net force on an object. The more net force I provide on something, the greater it's going to accelerate. So if I double the net force I place on something, it's going to double the acceleration. If I triple the net force, it'll triple the acceleration. And this is what we call direct proportionality. Since when I increase the force, it increases the acceleration, that means that force and acceleration are directly proportional. And we can write that like this. That little tilde symbol between acceleration and net force means acceleration is directly proportional or proportional to the net force. You can think of that in terms of a shopping cart. Obviously, if I apply a light, gentle tap to the empty cart, it's probably going to go a little bit. It's going to accelerate. But if I apply a slight, gentle tap to this full cart on the right, it might not even move. The acceleration for the same force I apply to each cart is going to accelerate the empty cart a lot more. It's going to be a lot easier to accelerate that empty cart than it is to accelerate the full cart. Now the second thing we want to look at in terms of acceleration, we know that force affects the acceleration. Now we want to see how mass affects acceleration. Force enhances acceleration, but mass resists acceleration. It opposes it. So again, acceleration depends on the mass being pushed. If I apply the same force to something with twice as much mass, I'm only going to get half the acceleration. If I apply if I apply the same force, if I apply the same force to something with 3 times as much mass, I'm going to get 1/3 the acceleration. Since when mass goes up, acceleration goes down, and when mass goes down, acceleration goes up, We call this relationship inversely proportional. So we could write it like this: acceleration is proportional to 1 divided by the mass. Notice as the mass gets bigger, that fraction gets smaller, meaning that the acceleration gets smaller. If mass gets smaller, that fraction gets bigger, meaning the acceleration gets bigger. So mass and acceleration are going to change in opposite directions. So let's relate all this together to get what Newton saw beyond what Galileo observed and came up with in his second law of motion. He realized that the acceleration produced depends not only on how hard we push, but also how massive the object is. And he put that in his second law. Notice here it's a little wordy. We're going to come up with a way to simplify that in a second here. His law states the acceleration produced by a net force on an object is directly proportional to the magnitude of the net force, and it's also in the same direction as the net force, and it's inversely proportional to the mass of the object. So not only is the amount of force I place on an object important to how much it accelerates, also important is the direction of that force. If I push something to the north, it's going to accelerate north. If I push it east, it's going to accelerate east. The more force I place on it, the more it's going to accelerate. Also, in the same respect, the more massive it is, the less it will accelerate with the force I place on it. Now that last way of saying it was a little wordy, so let's look at it this way. F equals ma. You might have heard that basic equation before. This sums up Newton's second law. Notice as the mass goes up, the acceleration has to go down if we want to keep that force constant. Likewise, if the force goes up, the acceleration would have to go up if we wanted to keep the mass constant. Another way to rearrange this to help us see what affects the acceleration would be A equals F divided by M, or acceleration equals force divided by mass. And remember that F, that force, is the net force. There's always going to be forces acting on an object, but what matters for acceleration is the net force, if there's a force that's winning the battle between the forces. So let's go ahead and look at an example here. How much force, also known as thrust, must a 30,000 kilogram jet plane develop to achieve an acceleration of 1.5 meters per second? So we know the mass of this jet plane is 30,000 kilograms. We also know that the acceleration we need to achieve is 1.5 meters per second squared. We want to know the net force needed by the plane. We know that force is equal to mass times acceleration. So we simply take 30,000 kilograms times 1.5 meters per second squared. And we're going to get an answer of 45,000. Again, remember, force is measured in newtons, so we're going to be saying 45,000 newtons because just by definition, a kilogram times a meters per second squared, since that's mass times acceleration, is going to give us a newton. But as long as you understand that forces are measured in newtons, you should be good. We have one more example here. What acceleration is produced by a force of 2,000 newtons applied to a 1,000 kilogram car. So in this case, we have a force of 2,000 newtons. We have a mass of the car of 1,000 kilograms. And we're looking for the acceleration produced. So acceleration is the force divided by the mass. So we would take 2,000 newtons, divide that by 1,000 kilograms. My zeros cancel out. And I'm going to end up with 2. And remember, acceleration, the unit for that is meters per second squared. So I'll end up with 2 meters per second squared in that case. So one major force we're going to see is friction. Friction acts on materials that are in contact with each other. You remember that diagram we saw. Even as smooth as you think a surface is, it's still going to have friction between the surfaces. There's still going to be imperfections on those surfaces. Friction always acts to oppose motion. It never enhances the motion. It's always going against that motion. And it depends on the surfaces that are in contact, the kinds of material that they are, and also how hard they're pressed together. If you lightly brush your hands against each other, there's not that much friction. But if you really force your hands together, it's really hard to rub them back and forth the harder you press them into each other. So not only does the type of material affect the friction, but also how hard they're pressed together is going to affect that. And just to give you an example of how the types of material affect that friction, a lot of concrete dividers are replacing the old steel rails on roads. And the reason that is because the friction provided between rubber tires and cement is a lot greater than the friction that's provided between the steel side of the car and the steel railing. So for cars to come to a quicker stop, if they run against that concrete divider, there's a lot more friction between the rubber tire and the concrete than there would be between the steel frame and the steel rail. So that's solid friction. There's also fluid friction. And fluid friction occurs in fluids, obviously, which can be liquids or gases, and it's as the object is pushing aside the fluid that it's moving through. One type of fluid friction is air resistance. This occurs when objects are moving through air. And anytime the friction ends up equaling the applied force, or the gravity, or any force you're applying, the object's going to end up moving at a constant velocity. You think of fluid friction in terms of movement in water. Obviously, water aerobics are very common because they provide more resistance for your body, more opportunity for your body to strengthen itself when you're moving through water. You also see air resistance, another type of fluid friction, when you're parachuting. That parachute provides a great amount of air resistance or fluid friction to slow you down. Again, once you reach the point where the force upward due to air resistance equals your force downward, you're going to go at constant speed because the two forces cancel each other out and you're no longer accelerating. This is called terminal velocity, and we'll discuss terminal velocity more in detail in the next part of this lesson.